Hi everybody, and welcome to another video brought to you by PLCGurus.NET. So you are now in the 12th installment of our ControlLogix PIDE Essentials video series, and if you haven't watched the preceding videos, please go ahead and do that now before watching this video, because we're going to get into some more advanced topics now. I'm going to be moving quicker through some of the sim panel controls, and what I ultimately want to do is start modeling dead time and lag time in our system. So in the last video, we experimented with the controller's reaction to a change in error. So i.e. a change in the PV, process variable, or set point, or by means of our external temperature disturbance, okay? And we also saw that the controller's response is dependent on its PID gain values. And we did go in here and we performed a manual tuning on this, okay? And we did leave it with an integral component of 0.001, and I thought that was a little bit too aggressive for what we were doing. We were at 0.01, which I thought had a nice smooth response, a nice fast response, and then we added a little more integral by making the integral gain component here a bit smaller, and we saw that we started to get a little bit of overshoot, and I think we were a little bit too rigid. But anyhow, we still had a nice, stable, fast response. And of course, we left the derivative at 0 for now because we are implementing this as a PI controller. And we also saw that the input had some time variability, meaning depending on how we hit it with a change or a change in error, whether it would be an impulse, a step, or we ramped the temperature disturbance, we saw that the response was slightly different depending on the type of error that we introduced into the process. And we did say that we can prove using some more advanced mathematical tools such as Laplace and Bode to determine exactly when our PI and D gains are going to push us into instability. Now, again, we omitted some of those more advanced tools, mathematically rigorous algorithms, in order to prove when these are going to happen, and instead we performed a manual tuning using the trend analysis. And also, I did mention to you that I have provided a PID tuning manual for you to download, and I'll include a download link in the comment section below so that you can grab both the sim panel and the PID loop tuning manual. Okay, so I think what we'll do is we're going to close this off now, and what I want to do is start playing with some of these DDT and LDLG simulation instructions to model dead time and lag time in our system, and then we're going to run through a very specific set of tests in order to observe the dynamic response under these different types of conditions. Okay, so to get started, I want to run through a series of, tests to try to model what the effects of the dead time and lag time is on our system. So remember, dead time and lag time are undesirable consequences of any given process. So it's our job as engineers, technicians, and technologists to ensure that when we design a system or a control loop, that we try to mitigate the effects or the impacts of dead time and lag time. So things like making your cable run shorter, making sure you have good PID tuning, these are all things that can help mitigate the effects of dead time and lag time. Okay, so to get started, what I want to do is I want to go ahead and tweak the gains just slightly. Based on the last video, I thought we were a little bit too aggressive on the integral. I'm just going to make the proportion a little bit higher at 3.3. And then again, the integral I thought was a little bit too aggressive. So I'm going to go ahead and dial that back to 0.08. Okay, I'm going to click apply. So now let's go ahead and head on over to the dead time and lag time instructions. So remember, in a real process, these are not going to be in your feedback loop. These are purely for modeling and simulation, okay? So the power of these things really is that it allows us to set up the complete control loop using the actual parameters or process dynamics or dynamics of our process. So, I mean, they're very powerful instructions in that regard. Okay, so let's go ahead, and I want to add in some dead time to our process. So I'm going to do that under the dead time parameter here, and I'm going to make this 2 seconds. So this is in seconds. I'm going to hit enter, And then I'm going to hit apply. Head on over to the LDLG instruction now, and I'm going to add some lag time into this instruction, and we're going to make it pretty significant. Let's add 5 seconds. I'm going to click apply and OK. Okay, so I think we're in good shape here. So let's go ahead and start up our sim panel. And you can see we're in hand mode. Our process is stopped, which is good. And I'm going to head on over to our trend. And let's get this going. So I'm going to click run. And we should see some things start up. Here we go. And you know what? I'm going to change this set point to 105. Because I want to leave a little bit of error in there before we actually kick it into automatic mode. Okay, so let's go ahead and start the process up now in hand mode. And you can see we're running. And let's go ahead and bring our PV up to 50%. So we're not going to bring it all the way to set point. We're going to bring it very, very close. And there you go. You see our CV. But notice now our PV didn't respond straight away. So we had an element of dead time in here. Did you see that? Remember in the last video when we had 0 dead time, 0 lag time, the PV response was immediate. But now we are seeing the dead time in here as well as the first order lag that we were talking about. So now you can see we have a lag time in here as well. And we did add a 5-second lag. So lag time is expressed in tau. So 5 tau is your total, or to get to 99.9% of your final PV position. Okay, so 1 tau, which is what we set, would be 5 seconds. So the total tau would be 5 times 5, which is about 25 seconds. Okay, and if we stop that trend and measure it now, we'll actually see that. So if you put a cursor on the screen, you can see the dead time will be identified. Let's just add another one, our active scroll bar. Let's do a delta. And we're at about 2 seconds there. And you can see here the lag time now, the total time is approximately 25 seconds. So remember, 1 tau is the lag time value we entered of 5 seconds. So in order to completely get rid of the error, that is equivalent to 5 tau, which gets us to about 99.9% of our final value. Okay, so a typical first order response, it really mimics the charging of a capacitor. If you've ever seen the charging and discharging of a capacitor. So you can see 27.5, but we're a little bit high there at 99. So we are around 25 seconds. So this makes perfect sense. We entered a lag value of 5 seconds, which gets us to 63.2% around there. And then the final value, 5 tau or 5 lags, would be 25 seconds. So right about there. Perfect. Okay. So let's run through this one more time. We'll go a little bit quicker this time. So I'm going to go ahead and just stop the process again. And let's go ahead and refresh the trend just by starting it back up. And here we go. Oh, so you see PV settling. So PV is going to settle out now because I did stop the process. So you know what? Let's let it settle out to its original value, and then we'll get a nice clean trend going. So we'll just wait for that PV to settle. And we're just about there, and it looks pretty close. So let's stop it and start it one more time, just so we have a nice clean trend here. And I'm going to go a little bit quicker through it now. So let's, so our set point's at 105. That's fine. So let's go ahead and run the trend. And you can see PV move just a little bit. So let's go ahead now, start the process, and bring it to 50%. And there we go. So we're going to get that same, there's our dead time, and we're going to get that same slow response that we saw previously, which corresponds to the lag time in the process. Okay, so we'll let that get pretty close there. And then what I'm going to do is I'm going to go ahead, once we get close to our, where are we? Let's just hover. Oh, we're getting there. Okay, so remember, it takes about 25 seconds to get to that final position of PV that we're looking for there, which is what we put in here. Okay, so let's go ahead now and hit it, put it into automatic or closed loop mode. So now our controller is automatically taking over, and based on the feedback, let's see what it's going to do here. So is it going to get us back to set point? You can see it's slowly getting to set point, and our valve is responding, right, based on the feedback. So it is responding. There we go. You know what? I'm just going to zoom this out a little bit. Let's go to our x-axis. Let's make this 2 minutes. There, then we can see everything in one shot. There we go. Okay, so now it looks like we're pretty good here. We're at set point. You know, we had a nice, stable response. But, I mean, we're dealing with the effects of dead time and lag time now, so it's not as quick as it previously was. So I'm going to go ahead and hit this now with a 10-degree disturbance and see what happens. So there's our step, a 10-degree C step. And notice now we're adding heat energy in from an external source. So our valve is closing. We don't need as much steam now in order to maintain set point. And you can see there we had a little bit of overshoot, but that dead time and lag time, that, you know, it's really having an impact now, isn't it? You see that overshoot, and now we're slowly getting there, but we still have stability. We are still able to recover from an excessive dead time and lag time in our process. So I'm going to stop that there, and that's pretty good. That looks really good there. So I'm just going to label this because I'm going to save this out actually. I'm going to double click there. I'm going to call this, I don't know, what do we want to call this? Let's call it loop parameter. Actually, you know what? Let's just put our loop parameters in. So I'm going to say we had a KC equal to 3.3. We have a tau sub I equal to 0.08. And we have a TD, a derivative of 0, because we're implementing as a PI controller. And we have a dead time in this one as of 2 seconds. And we have a lag time, we'll just call it lag, equal to 5 seconds, right? And let's just label that, okay? And you know what? I like that. Okay, let's go ahead now and you know what? Let's increase the dead time significantly and see if we still have some stable recovery with these gains. But before we increase the dead time, why don't we use the window snipping tool here just to grab a quick snapshot of this trend, just in case we want to refer back to it. So I'm just going to go ahead and grab a snapshot of this guy. And there we go. And there we go. Now we can refer back. We can see what it is. And let's just save this as DT2. I don't know. We'll put it in pictures. That's fine. Just in case we want to refer back to it later. All right. So let's go into our loop control routine now. And let's bump up that dead time. And I'm going to make it this time. Let's make it 5 seconds. 5 seconds? You know what? Let's make it 8 seconds. Let's make it extreme. So we should really see this dead time now in our trend. So I'm going to click apply. And let's check here. So we're still okay. We made our storage array 100 elements. And with an 8-second dead time, it's telling us we need 80 elements. So remember, the way it's creating this dead time is rather than feeding the values directly back to the controller, what it's doing is effectively pushing these onto a stack in the instruction, in our array. And then it's popping those values off the stack, feeding it back at the interval that we define, which is 8 seconds. Okay, so I hope that's clear how this thing is actually working. All right, so let's stop the process now. Let's put it in hand mode. Let's zero out our temperature disturbance. And let's head back to our, oh, we're not quite there, a little bit more, and there we go. Let's head back to our trend, and we should see, let's go ahead and start it, and we should see everything settling out again. So let's let it settle out. And there we go. So we're watching it settle. And you know what? I'm going to pause it just because we don't have to sit here and watch PV move back to where it should be, and then we'll come back. Okay, so it looks like PV is settled out now. So I'm going to go ahead and just stop the trend and start it again. And this time I want to run through it exactly the same way we just did, but notice the effects of the increased dead time now. So let's go ahead and start the process. And let's put our value in 50%, which corresponds to 97.5 degrees C. And there we go. We see CV respond immediately because we're in hand mode. So we're taking direct control over the position of that valve by entering a value in CV hand. And there we go. So notice now we do see that increase in dead time here, don't we? So that increase in dead time corresponds to the 8 seconds that we just put in there. Do you see that there? Okay. Are we going to be able to still put this in automatic mode and still have some stability? That's the question. All right, so let's see what happens here. So where are we at? We're pretty much at, so we're pretty much there. We're at about 99%. So let's go ahead and kick this into automatic mode and see if the controller can recover now based on that longer dead time. So remember now, dead time, the negative effects of dead time are that we are making changes, but we're not seeing what the impact of that change is until some period later, 8 seconds later, which could cause issues, right? We're making a change in our output, our steam, but we're not seeing what the impacts of that change are straight away. We're seeing it some period later. So we're compensating by moving the valve because we're seeing the temperature isn't changing straight away, and we're overcompensating. So this is what we're seeing here. See how we're overcompensating here? Because we're not seeing what the impact of adding more steam had on our process. And that's why dead time is a very, very bad thing, because we are changing the output but not seeing what the result or the impact of that change was. And you can see here we are going into instability almost straight away. And if I hit this with a disturbance now, let's go ahead and hit that with a step of 10 degrees C. And let's see what happens. So, I mean, it's already gone. I mean, there's no way this is going to recover. Let's just zoom out a little bit more. I'm going to go to 3 minutes just so we can see more of this trend and watch this function grow. And there we go. So we're seeing the effects of dead time here. When we did have stability with the gains that we had, by adding more dead time, we can see that this thing is just oscillating uncontrollably now. And this brings up a good point with dead time and lag time that I'll talk about in just a minute. Let's just watch what this thing does for a minute. So you can see here this function is growing. And basically our valve is just oscillating uncontrollably, and it's basically going to only be limited by the physical hard stops of the valve itself. I mean, it can only move so far. So this thing is just smashing open and closed continuously, which eventually is going to obviously blow the steam valve apart. Or if this is being indirectly driven, I don't know. But either way, this is going to cause some severe damage to our instruments and our devices in the field, our final control elements. So this is a bad thing. And we can see the negative effects. I'm just going to stop before we lose this. You can see what the negative effects of significant dead time are. So let's go ahead. I'm just going to rename this now. And so we can grab, just in case we want to refer back again. And let's grab our snipping tool. And let's grab a snapshot of this as well. Good. Yes. All right. Let's save that. And we'll call this one DT8. So this is an 8-second dead time. All right. Perfect. All right, so we're doing good here. So I want to take a minute now to talk about something. So we can get a measure of how easy or difficult a process is going to be, or a loop is going to be able to be controlled by looking at the dead time and the lag time in the system. So, and we can take a ratio of the two. So if the dead time to lag time ratio is significantly less than 1, then we can say that the process is relatively easy to control, meaning we should be able to get this process into some kind of stable response. If the dt over tau or lag time relationship is some value less than 1. If the dt over lag time, the dead time over lag time ratio is greater than 1, which it is in this case. So look at dt over, or 8 over 5 is some value greater than 1. Then we say that the process or the control loop is hard. It's hard to control. It's a difficult process to control. So it's a good guideline to go by. If your dead time over lag time is less than 1, you should be able to control it. If your dead time over lag time is greater than 1, you're going to have some problems controlling that process, okay? And you need to employ some tactics in order to get the dead time lower, all right? I hope that's clear. Okay, so you know what? I think this video is getting a little bit long. So we've seen the negative effects of dead time. We've been able to model our dead time and lag time in the process using our DEDT and our LDLG instructions. And we've seen that when the DT to lag time ratio is greater than 1, that we are in a region that is very difficult to control. And we can see that by our trend that we are going into uncontrollable oscillations. So in the next video, what I want to do is I want to see if we can make use of the auto-tuning function of the loop controller and see if we can actually, if the controller can find a set of ideal gains that will get us and tune us out of this excessive dead time and lag time and get us into some kind of stability, controlled response, okay? So stay tuned. We're just about there. We're gonna do some auto tuning in the next video. Please, if you've been following along and you're liking these videos, please do like and subscribe to our channel, and please share these videos as well. We are trying to build our community, and head on over to https://PLCGurus.net and become an active member in our community over there. So again, I want to thank you for watching, and I'll see you in the next video. Thank you.